Hi everyone, I think we can start with the session now. So, hi everyone, this is Manish Nath from Hex-Star universe, and I am going to be your host for this session. First of all, thank you everyone for taking your time to join us today. Now, our topic for today's session is CFD, Computational Fluid Dynamics of Rocket Nozzles. And to enrich us on this topic, today we have none other than Ms. Nivedha Govindarajan. She is a graduate engineering trainee at TAS and also completed several internships on designing and CAE. We are really glad to have her here with us today. So, without any further ado, I'd like to request Ms. Nivedha to proceed with today's session. Thank you, everyone.
Thank you, Manish, for the wonderful intro. Uh, just a second. Can I just present?
Yes, surely.
I hope it's visible to everybody here.
Yeah, it is visible.
Okay, cool. So, good evening, everybody. This is Nivedha Govindarajan. I am an aerospace engineering student. I was an aerospace engineering student, currently working at Rocket Aerospace Systems as a graduate engineer trainee. My interest lies in rocket propulsion, being that's my major in my college too. As a fresh graduate, whatever knowledge I have, I would love to share it with you guys. If any mistakes do come up with suggestions, or if I made a mistake, do correct me. Warning you guys in prior. So quickly getting into our session. What are rocket nozzles? A nozzle is a pipe or a tube that can accelerate your flows, and it is a pipe or tube of varying cross-sectional area, and it is used along with a rocket engine to accelerate hot exhaust to produce thrust according to Newton's third law. So your Newton's third law always says every action has an equal and opposite reaction. So as and when your propellants burn, it gives out the exhaust, and then your nozzle is pushed forward. Your rocket is pushed forward with the help of the nozzle, producing the thrust. Thus, the basic working of the rocket nozzle goes like when the air is flowing through the diverging section. We have two sections in a nozzle. Firstly, convergent and a divergent. Both are connected through a portion called a throat. We will come to that topic on what should be the throat, how it will be, etc. later. But first, we have this throat, and when air is flowing through the divergent section, there is an increase in kinetic energy, and there is a drop of enthalpy. If you guys are into chemistry, you will know what enthalpy is. So there is an increase in velocity and decrease in pressure at the exit of your divergent section. So this is your very basic working of your nozzle. That is just the skeleton of it. Okay. So next will be what are convergent divergent nozzles used for? They are used for generating supersonic desired properties you want. You can, if you want a mark of 2, it is achievable. If you want a mark of 3, achievable. Anything above 1 is achievable, as well as even if you want a subsonic wave for a subsonic nozzle, that is also achievable by the same nozzle theory, which we will be discussing later. Okay, cool. Now, what is CFD? CFD is, as you can all see it on your screens, it's a branch of fluid mechanics. It uses numerical analysis to solve problems. So how do we solve problems? We are going to use our very old formulas like the Bernoulli's theorem and pressure equations, velocity equations, Navier-Stokes, etc. To solve a problem, which is your flow through your nozzle is your problem here. You want to know how your flow goes by inside your nozzle, so you use CFD. I hope it's clear. So this is very basic of what is CFD. So how do you make a rocket nozzle? Now this is, I guess this is interesting. Uh, we make a rocket nozzle starting from the nozzle theory. Your nozzle theory is just how a nozzle works and where do you start designing a nozzle. And why do we need a nozzle design? To accelerate the combustion products to a high exit velocity. And you have to have a necessary geometric profile. For example, your throat, which I was talking about, which connects the convergent and the divergent portion, its mark should be equal to 1, which is also known as the choked flow conditions, which will make the air to accelerate to a supersonic Mach numbers. So, how are you going to design the nozzle? Whenever you're going to design a nozzle, you're going to fix your throat diameter. Say, for example, you're having a throat diameter of 50. Afterwards, you use all the equations of etc. for your inlet and your outlet diameters. So we start from the throat, we go to the inlet, and we go to the outlet. We use the very basic stuff called area ratio, which is AE by AP, A area to exit to area of throat, because we have the throat area, then we'll get the outlet area. Using the same thing, you'll get your inlet area too. So that's how your basic geometry is done in your nozzle. And let me tell you one more thing. There are two types of nozzle. One is the straight CD nozzle, which will not have any curves in between or bells in between, something like that. And another is a D level nozzle with a slightly curve to reduce your shock waves. We have this thing that is, so if you have a shock wave inside the nozzle, it is called inefficient nozzle because your flows will not accelerate to the given Mach number at any cost. So your goal is to reduce shock waves into a nozzle. And how do you know where the shock wave is formed inside a nozzle? Using your CFD. Is the geometric. So the geometry, as I said, is done by fixing the throat, then getting into the inlet diameter and the outlet diameter, which depends on the pressure which you want to give to the nozzle. For example, the nozzle which I built here with a 5 bar pressure at the inlet, and we needed it as an optimum expansion, that is no more pressure or less pressure than the atmosphere, which will give us a proper nozzle efficiency. If you want a 100% efficient nozzle, it has to be, then your next point is after you're done with the geometry, you have your 2D stuff. You have just your 2D drawing. That is, you have 6 points, like the throat 2 points, the inlet 2 points, and the outlet 2 points, like this. So you're going to make an outline of it to get your geometry. After you're done with your geometry, you will just get a straight CD nozzle, which we will come back to that later. Now we are just sticking on to the geometry. So that is your geometry. But your geometry is not yet complete till such time you divide those into portions. When you divide them into portions, the software finds it easier to compile or compute the results which you want. For example, you want to see how a flow changes at the throat. So you need the throat portion to be cut separately to identify what the characteristics are changing or how the characteristics are changing. So you divide them into 4 portions for the ease of the software. Okay, that comes to your geometry. I am not getting into the working of the software and all. I'm just getting into very basics of CFD and how you make a nozzle or how I made a nozzle. That's it. It's just that basic. Good. After you're done with the geometry, there's a solver which allows you to do your meshing. As I said, we want to get to know the properties changing at the throat. So when you're at the throat, you will see a huge change in your contours. So that is where your pressure decreases, your Mach number velocity increases. When velocity increases, your Mach number increases. All these happens at the throat. Till such time, it's just a normal progressive. Okay, since we are in the topic of meshing, we should know this. Meshing is actually why it is done is because we have to capture the airflow which that behaves along the flow domain. We have to capture how a flow behaves through the domain. Okay. And for better results or better accuracy, you need the meshes to be finer. They have to be really fine so that you know even the smallest of the smallest changes. As I told, it is divided into four phases. So 1, 2, 3, and 4, and then you can see the meshing which I have done over here. The throat and towards the wall there should always be a thicker mesh or finer mesh because that's where your properties change. As said, in the throat your properties change, and towards the walls there can be viscous elements to it. Though here I am playing only with compressed air. If you use it on a later date, the same nozzle, if you use it on a later date for any propellants, any LOX, LOH, anything, you will be considering viscosity along the walls. So to notice how your airflow or your behavior of flow changes along the walls, you make the mesh towards the walls thicker or finer. Uh, as I told, the throat mark should be 1. So to achieve that 1, what I have done is a small curve of radius of 50 mm so that I can get rid of the shocks. When I did a straight CD nozzle, there was a huge shock interaction in my Mach number contour, which would have drastically reduced my outlet Mach number. So to avoid that, what we do is make a gentle curve. So this does not belong to D level nozzle, but it is still a straight CD nozzle, but just a little bit curved. That's it. It is only to eliminate your shock formation. Okay. Here I have number of nodes amounting to 1 lakh because that is when the solution is considered accurate or proper. Any node numbers below 1 lakh is considered that you can make it more accurate, etc. So after this is done, our one more main part before the post processing is that you'll have to give named selections for your nozzle. For example, this becomes your inlet. Okay, and this becomes your throat. These becomes your outlet. The other portion should be named as walls. There are if you're naming it walls, it will act as a proper wall. It does not let any of your outside atmosphere air to affect the flows inside. That is the literal meaning of wall. So you're going to name all these as walls, all the leftover portions as walls. So for the exact same reason which I told. Okay, coming to the post process. You can see your contours here. Before that, I would like to touch upon a few points, which happens to be what are the models I used and all of that. So I used a density-based solver because pressure-based solver is not used in any of the aerospace applications, or even if it is used, it is not preferred or not accurate because of so many reasons. I have used density based analysis or density based solver, and then I have used energy equations to know how much temperature changes is happening in my nozzle. There are so many viscosity models. Like I have used SST K omega. There are a few more, Spallet Almaraz, and normal models, etc. are there. But I use SSTK omega for a number of reasons, which I will be saying now. The SSTK omega is a two equation model. Okay, we have two equations to solve, which gives you better accuracy again. But Spallet is a single equation model. So what you use is SSTK omega model, and then it gives you superior performance and a great pressure gradient. It is also suitable for viscosity models, that is viscosity elements. Here it is air. If you use any other propellants, you'll have viscosity. It is also suitable for that. And you use for aerospace applications, we use Sutherland viscosity. And my operating pressure is 0, but my inlet pressure will be 5 bar at this point of my nozzle. Okay, so then we go ahead with the viscosity model, and then you set all the parameters like your inlet conditions, your outlet conditions should be 101325, that is equal to your atmospheric pressure, so that you get an optimally expanded nozzle and everything. And your gauge pressure, that is your total pressure, should be set at 5 bar plus your 101325. Your gauge pressure is the total of all the pressures which you are using in your solver. Okay, so then we go to the solution controls. Yeah, we have the solution controls, and we iterated for around 5,000 to 6,000 times. So during the iteration, you can see a number of residual plots like the nu t, x velocity, y velocity, etc. in your screens, which I don't have it here, unfortunately. But yeah, you get a residual plot here, which tells you the various nozzle parameters that are extracted during the iterations. So okay, and when you run the iteration and the solution meets the conditions which you have given, that is your output conditions, that is when it is said that the solution is converged. So when your solution is converged, that's when your nozzle is ready to show you the contours. Till then, it was always an underdeveloped flow or something like that. Here we can see on your left is your pressure contour. At the beginning, we have a 5 bar pressure, but as and when it goes through the nozzle, you can see that the pressure decreases. And as pressure decreases, your velocity goes up because they are inversely related. Same inversely related, and here we have the lowest velocity. And you can see that during the throat, you get a mark of almost 0.92, which is close to 1. Yeah, though not there yet, this needs to be iterated more, but this is 1. You have to have a 1 to develop a supersonic Mach number. Otherwise, your Mach will remain below 1 itself, or it won't even reach supersonic Mach. So my exit Mach number is 2 at this point. And then if your exit pressure is greater than the atmospheric pressure, the nozzle is said to be underexpanded. And if the exit pressure is less than your atmospheric pressure, it is said to be overexpanded. So I don't want either of the two. I want just optimal conditions for 100% accuracy. So we have the contours here, and the next we have our flow domain analysis. Why do we do this? So that we can check if your shock wave is forming outside the nozzle or inside the nozzle. Okay, so here we don't have a shock interaction. We do not have a shock interaction in any of these, proving that the nozzle is quite sufficient or efficient enough to provide the given mark, which is almost 1.8 to 2. If we have had a shock interaction over here, there wouldn't have been a mark of around 1.8 or 2, but it would have been around 1.3 or 1.4 for sure. So here we check that only. If my shock formation is outside the nozzle and my shock diamonds are very much outside the nozzle as said. Yeah. So I'm giving the whole presentation. Sorry guys. Sorry. So velocity contours here are seen. Here we give these as our walls again. Only these are the walls and these are also the walls. These are inlet, throat, and this will be your outlet. Only that is the change in that. All your other conditions are going to remain the same. You're going to have a more number of iterations because you will be making it along a flow domain of almost 3,000 mm. So this length is around 3,000 mm. So that is your flow domain. So here we can see that the velocity outside is increasing because like there's a shock formation outside. And since these are the walls, there is no effect of the outside air on your nozzle flow domain. Okay. Say similarly with your pressure contours. Here it doesn't matter much whether you given it walls or anything. One point I would like to make a note here is if you give these as far field far field domains, then far field is such a thing like they are walls, but they are walls made of air. So and walls are walls. So that is the only difference between far field and walls. Since far field is also a wall made of air, it might affect the flow over here. Like this area will get affected more because it's a far field domain. Okay. So we have compared a lot of our analysis with the NASA results and stuff like that. So NASA and other industry made nozzles just to check the efficiency of our nozzle. And we have come up with so many conclusions that our nozzle is perfectly efficient enough to and it is all this nozzle project. So we vectored it to see how much thrust we get when we vector it, like when we move the nozzle or when we tilt the nozzle to some extent. We have plotted a various number of graphs like area ratio versus the Mach number plot, area ratio versus pressure ratio versus Mach number, and of many plots. And if you guys want to learn many other things about nozzles or how it works, I would suggest Radhakrishnan book is going to be your Bible. And probably this is the shortest session you guys would have heard, but I'm sure it would have been a little bit informative. So that's it from my end. So over to the organizer.
Thank you, Nivedha, for this wonderful presentation and the session. So now I think we can move on to our Q&A session. So participants, if you have any questions, you can either turn on your mic and ask your questions directly, or also you can write in the chat and we will ask out the questions.
I'm audible. Can I ask a question?
Yeah.
Ma'am, you understand Hindi or not?
Yes.
मेरा ये सवाल था कि जैसे अभी आपने रॉकेट का नोजल बनाया था, तो अगर शुरुआत से एकदम स्क्रैच से बनाना हो किसी सॉफ्टवेयर के माध्यम से पीसी के अंदर, तो कौन से सॉफ्टवेयर हमको यूज करने पड़ेंगे और क्या-क्या बातें हमें ध्यान रखनी पड़ेगी? प्लस कौन सा मटेरियल यूज करना पड़ेगा? जहाँ तक मुझे मैंने रिसर्च की है कि नोजल का जो हीट, वो जो गर्मी निकलती है रॉकेट के इंजन से, वो बहुत ही ज्यादा होती है, पिघल भी सकता है, तो इस वजह से कौन सा मटेरियल यूज करना चाहिए, यही मेरा सवाल है।
ओके, अगर आई होप एवरीबडी हियर अंडरस्टैंड्स हिंदी। ओके, सो अगर आपको डिजाइन करना है रॉकेट नोजल स्टार्ट से, तो आपको तो पहले नोजल थ्योरी परफेक्ट करना ही पड़ेगा, ऑफ कोर्स। सॉरी, या आपको तो नोजल थ्योरी परफेक्ट करना पड़ेगा, एंड एज आई सेड इन माय प्रेजेंटेशन इटसेल्फ, वी आर गोइंग टू फिक्स योर थ्रोट, and after you're done with all your calculations, you reach your 2D geometry. वो 2D ज्योमेट्री को आप ANSYS सॉफ्टवेयर में डाल के यू कैन डू द सेम कंप्यूटेशनल फ्लूइड डायनामिक्स ऑफ व्हाटएवर आई हैव सेड टुडे हियर, आप उसको इस्तेमाल कर सकते हो, एंड इफ योर सिमुलेशंस आर राइट देन यू कैन गो अहेड विथ योर फैब्रिकेशंस। आप फैब्रिकेशन को करने के लिए यू कैन यूज एनी कैड सॉफ्टवेयर लाइक केटिया, सॉलिडवर्क्स, सॉलिड एज, anything that comes to your mind, even Fusion 360 is welcome. आप वो करके आप फैब्रिकेट कर सकते हो। सिंस आई यूज्ड कंप्रेस्ड एयर फॉर माय एक्सपेरिमेंट, मैंने उसको स्टेनलेस स्टील से बनाया था। आप चाहते तो आप एल्यूमिनियम से भी बना सकते हो, क्योंकि इट्स अ वेरी गुड इट्स अ वेरी गुड अलॉय बेसिकली, एंड इट इज इजी एंड इट्स लाइट वेट टू। तो आपको अगर स्मॉल स्केल में बनाना है तो you can use either aluminium or stainless steel as said. And one more important thing to note is your propellant is going to decide your material of the nozzle. I hope I cleared your doubt.
हाँ, लेकिन जैसे अभी आपने बताया कि वो आंसर का कुछ सॉफ्टवेयर के अंदर एक करना पड़ता है, वो 3D क्रैट और फ्यूजन 360 वो सब कुछ बाद में हो गए, वो कौन सा सॉफ्टवेयर था, वो आप उसका नाम वगैरह ऐसा कुछ होगा तो आप चार्ट में टाइप करके बता सकते हैं? प्लस अभी जो आपने आंसर बताया था वो इंग्लिश में, क्या आप रिपीट कर सकते? किसी ने वो इंग्लिश में पूछा है, जो आप चाहिए था किसी को। थैंक यू।
अच्छा, तो ANSYS सॉफ्टवेयर है, आई पुट इट डाउन इन द चैट बॉक्स, just, and also the book name was Gas Dynamics by Radhakrishnan.
आखिरी सवाल मेरा, अगर पॉसिबल हो तो ये मीटिंग खत्म होने के बाद किसी के मन में कुछ सवाल आता है या फिर कुछ प्रॉब्लम आती है, तो आपसे कांटेक्ट कैसे कर सकते हैं? ईमेल आईडी या लिंक्डइन आईडी जैसा कुछ होगा तो जैसे आपसे मैं या फिर कोई भी दूसरा कनेक्ट करके मार्गदर्शन पा सके इस मामले में। थैंक यू।
Yeah, so LinkedIn is Nivedha Govindarajan. I'll put it down. That's my LinkedIn ID. और या फिर email should be this. Yeah, it's there in your chat box, everybody, if you have any further doubts. Next, anybody else?
Hello.
Yes.
Yeah, can I ask one question? I have one doubt. Yeah, while designing or while analyzing the nozzle, if we are using we know that it is exposed to a high temperature around above 1000 degrees. Then is there any way to avoid such a tolerances for the thermal expansion and all in the analyzing part? of the nozzles.
Yes, yes, you can see how temperature varies along with your nozzle. There is a provision to check your Mach number, your velocity, your pressure, your density, your thermal, your temperature. Uh, Anything you ask, you can even your force across the nozzle can be measured using the same ANSYS software, which I'm talking about. So, if you really want to see that how much temperature your nozzle is using, then all you have to do is run the same procedure what I told. Just run it, and instead of putting it to Mach number or pressure, put it to temperature. It will show you the same contour. It will give you results. It will give you even data which you can plot it for your convenience at your convenience in your Excel sheets. I hope I answered your question.
Yeah, it's clear, but I asked that the temperature, the velocity of the flowing fluid is also depending with the temperature, and also the material property
Yes.
material property may changes, or the material may expand or contract with the effect of the temperature. Is it can be analyzed by the software?
You're asking about the material, right? Like
Yeah,
how the material will be able to sustain it or not. Is that what you're asking?
yeah.
Okay. For that also, same ANSYS can be used, but with FEA. Finite element analysis. You can subject it to temperature loads, pressure loads, etc., to know if your nozzle will be sustaining so much of a higher temperature. So how you can go about this? You're going to put your nozzle in your ANSYS solver. ANSYS as in your what is that CFD solver, where you get your highest temperature depending on your contour or your inlet outlet conditions. Okay, you understood till here?
Sure, clear.
Yeah. After this, you have your highest temperature. So what are you going to do? You're going to go to static structural analysis and
Okay.
put the same amount of temperature load on your same 3D design and check if it is able to withstand it. Okay. If it doesn't withstand, you're going to change your material. Cool?
Okay, thank you.
Yes, by FEA, pressure can also be calculated. No, pressure cannot be calculated. Pressure can be applied. This was the answer to Jiva B. And for BK gaming, which nozzle is best, D level or CD? Hands down D level, because all the rocket industries use D level. If you ask why not CD, I haven't researched to that level yet. When I get an answer, I will definitely let you guys know. Hello, speech was nice. Any idea to continue this session to next level? Like another session or any? Thank you. That depends on the organizing committee. And if you guys really like my speech, you can recommend if you really want to visit or something like that. I would be really happy to deliver more lectures on the same topic. Why plus for this meshing? I didn't understand your question, Akshay. Can you please unmute and ask? Yeah. Are you trying to ask that why do we need to have a structured mesh or unstructured mesh, or why it has to be thicker at the walls or at the throat? Is that what you're trying to ask? Okay, first I'll answer Akshay's question. We see a lot of changes in behavior of the flow properties of the air at the walls of the nozzle as well as the throat of the nozzle. So if you want to capture those little changes in your flow, you have to make the mesh finer at those specified points. Got it? Akshay? Okay, so pressure contour and mark contour of 3D nozzle is in a pressure contour is not inversely related. Pressure is inversely related to velocity, that too not mark. Pressure is inversely related to velocity, and when velocity changes, your mark also changes because you know the equations, right? Any other questions? And Akshay, if you're asking, well, just 1 second, sir. If you're asking y plus, which is the non-dimensional value, it will be your first cell height, which means when we use your number of elements, you use bias. Is that I really didn't understand your question, so I'm just all over the place right now. So whatever I know, I'm answering.
मेरे 2 सवाल है आपसे, आखिरी 2 सवाल है परमिशन है?
हाँ.
कि पहली बात तो कि आपकी जो लिंक्डइन आईडी की लिंक है ना, वो आप शेयर कर सकते चार्ट में, वो अच्छा रहेगा, क्योंकि आपके जैसे ढेर सारे नाम और भी हो सकते हैं लिंक्डइन पे, ढेर सारे और भी अकाउंट हो सकते हैं। पहली बात ये। दूसरी बात ये कि पॉसिबल हो तो क्या बोलते हैं, रॉकेट का जो लिक्विड इंजन होता है, उसके इंजन बनाने में सॉफ्टवेयर कौन से लगते हैं कंप्यूटर के या पीसी की मदद से ऑनलाइन, तो उसकी पूरी अगर आपके पास लिस्ट वगैरह ऐसा कुछ हो तो वो आप उसके नाम दे सकते हैं चैट बॉक्स में, क्योंकि मैं और मेरे कुछ दोस्त एक संस्था के अंदर रॉकेट इंजन बनाने की कोशिश कर रहे हैं लिक्विड इंजन का, तो हमें वहाँ पे बहुत ही परेशानी आ रही, इस वजह से आपका मार्गदर्शन चाहते हैं इस पे। थैंक यू।
इंजन्स का मेरा उतना अभी मैं गई नहीं हूँ, अभी मैं रॉकेट पे ही मैंने पूरा काम नहीं किया है, मैं इंजन से पहुंची ही नहीं हूँ। But for sure, if I come across anything, I will connect to you through LinkedIn and I will let you know. But as said, the best software which you can use is ANSYS and any mechanical design software for any of your work. And ANSYS is like the Bible for your any CFD flow analysis or even your FE. So if you're going to learn something for your propulsion, it has to be first ANSYS according to me. Okay. Does ANSYS software support whole rocket design and testing? Whole rocket design, I doubt. If you're talking about only parts, like part by part, so if you do it part by part, yes, you can. For the whole rocket design, you can do your stress analysis. For your avionics bay, you can do electrical analysis. You can even do your harmonic analysis using your ANSYS. For the nozzle, you can do CFD analysis and static structural to hai and stuff like that. And if you want to choose your propellants, there is a very good software called software name. It's an open source kind of stuff, which is NASA CEA software, which is useful for propellants. You can play around with your propellants, your chemical equations, balance it out, and then choose the right amount of propellants you want to use. So, and then with those qualities of propellants, you can come to your ANSYS, do your CFD. With those, you can do your structural. So that's how your rocket design is going to work. I guess I answered your question.
Thank you. क्या वो नासा का जो आपने सॉफ्टवेयर बताया उसका नाम चैट बॉक्स में लिख के दे सकते हैं आप? तो थैंक यू।
Yeah. NASA CEA. आप अगर इसको सर्च करोगे तो पहला लिंक आएगा। तो या Which type of mesh do you prefer for the normal mesh? इसमें कोई प्रेफरेंस नहीं है. जो मैंने किया वो बस it was just a trial and error method. Since it was just a 2D drawing, I just did it by the number of element method with bias, reverse bias, and that's it. I don't know what I just made it a mesh which has to be fine. That's all. I guess that's it, right?
Yeah, I think
Any other
that's
question?
all of the questions I've got. So, participants, if you have any other questions, please feel free to ask. And also, please don't leave the meeting because we will be distributing badges for this session. So please stay in the meeting.
For Tushar, this is your NASA CAE software ka link also.
Well, I think we don't have any other questions here. So, okay, someone have asked, Dhruv Bharadwaj have asked, ma'am, I am a 12th pass out student. What should I do to pursue this CFD?
Pursue the CFD. Okay. For that, you'll have to learn basics of aerodynamics, starting from Bernoulli's theorem, Navier-Stokes equation. Start slowly. During your engineering level, you can start with your softwares. That is my personal advice, which I would love to give.
Well, participants, if you have any other questions, please feel free to ask.
Resources for aerodynamics. Yeah, honestly, whatever aerodynamics I learned was from my teachers. I never used any books or something. But specifically for rockets, I don't know. I really don't know. If I get it, I will definitely let you guys know some or the other way. So yeah, if you're being taught Bernoulli basics, then try building upon that. And
Well, I think we
yes,
don't have any other
Abhimanyu,
questions.
thank you.
Well, I think we are done with the Q&A session. I don't see any other questions in the chat. So I'm really sorry that I'm facing some internet issues, so I couldn't interact much throughout the session. And also, thank you, Nivedha, for this wonderful presentation and helping us out and enriching us on this topic. And I think every one of our participants have been really helped and learned a lot about this topic. And also, thank you to all our participants for making this session a successful one and supporting us throughout the session. And lastly, I would love to request everyone to turn on their camera once so that we can take a picture for our memory purpose. Thank you everyone who have taken the pictures, and now we will share the link for the badge. So please wait for a minute and we will be sharing.
Okay, thank you, Manish and Vani ma'am for giving me an opportunity to interact with people. So I'll take a leave right now here.
Surely,
Thank
it was our
you.
pleasure to have you here with us today. Thank you for
I
giving
know
us.
I wasn't up to the marker probably that. Yeah, but I did what I knew. Thank you. Bye.